this topic. Okay, and then in later 2010, Greg Engel at Chicago and Greg Scott at University of Toronto, they also measured the other. This one is FMO again, but this one is photosynthetic compounds from a marine algae. And then they also see this beating signal at room temperature. Okay, so this one, the first experiment was done at 77 K, and the most severe criticized at that time was this is not anything meaningful to biological systems. 77 K is too low in temperature. How about in room temperature? So they performed the measurement. This is really at room temperature, 20 degrees Celsius. And this is results from Greg Engel's group. So they changed temperature from 77 K, that's our beating, to 277 K, this red line here. Okay, so 277 K is probably not room temperature here, but probably is the room temperature at Chicago. Who knows, right? But you see dephasing, you see the decrease of coherence, but at 277 K, you still see beating, meaning there's still quantum wave-like evolution in the system. This is some more details of their result, and then lots of publicity is gained at that time. Some people call it the dawn of quantum biology. I'll come back to this point later. So that's give you some introduction and some kind of a historical background on this subject. But then I want to go into a real system to talk about what I think really is the quantum effect that's been utilized by photosynthetic systems. Let's look at a specific example called LH2. I'll show you the structure before already. So this picture, I already showed this picture before. Okay, those are LH2, ring-like, very beautiful structure. And in this case, this is the sunlight spectrum that I already shown, and those are absorption of all sorts of photosynthetic pigments. And the bacteria, they actually occupy this region. They occupy here, from 700 to 900, around this region. Okay. So actually, all range of sunlight is being utilized by all sorts of different organisms. It's remarkable. So they evolved the bacterial chlorophyll to harvest sunlight in this region. This is a spectrum of photosynthetic membrane from bacteria. So this is that membrane has been taken out, okay, from that. So that kind, it has LH1, LH2, and reaction center in it. Now, if you look at this absorption spectrum of the membrane, and people have done lots of work to decompose this into its components. So there are three pigment protein complexes here, LH1, LH2, reaction center, corresponds to LH2, shows you these two peaks, B800 and B850. Named such because this is 800, this is 850, the peak position. LH1 over here, B875, and reaction center is much smaller. You couldn't see it. It's been covered by all those two bands. Okay, but people can decompose it quite nicely into this. And energy transfer has a very well developed funnel. It's very easy to understand, going from high energy to low energy. So light energy absorbed at 800 funnels to BA50, and from BA50 goes to BA75, the large ring. Maybe let's go back here. So this 800 outer ring to A50, A50 to A75, and then to reaction center. Okay, so a very well developed funnel that facilitates the energy transfer. And then to the reaction center, position at reaction center called P spatial pair here. This is a real structure of this LH2. It has a 9-4 symmetry. Each individual component is like this. Okay? And each one contains 3 bacterial chlorophylls. If you look at the arrangement of bacterial chlorophylls, there are two rings here. The outer ring is BA100, the inner ring is BA50. BA100 is kind of loosely packed only, so they are far away from each other. The distance is around 20 angstrom. But the BA50 ring are closely packed. So the distance from here to here is just 9 angstrom, very close to each other. Instantly, you should pick up that, so the coupling between BA100 pigments are small, but coupling between BA50 pigments are large, significant. Now, let's look at the BA100 intra-ring excitation energy transfer. The coupling between them, between neighboring BA50 rings, are around 300 wave numbers. That's a large number in photosynthetic systems. So the acetone states, so the localization of excitations is severe, is very important in this system. Okay. Although there is so-called static disorder, because the protein is kind of a soft system. At each protein, the energy of each chlorophyll here can vary a little bit. Okay, that introduce some sort of disorder in energy and localize the states. But if we use a perfect ring to describe the system, you have all those different states, K0, K plus minus 1, plus minus 2 states. Those are couplings calculated from different methods, but generally the qualitative structure is the same, so the quantitative numbers are not very important here. If we overlap this with BA100, BA50 and BA100 absorption spectrum, you see that BA50 actually are coming from, absorption are coming from this K equals minus plus minus 1 back, these two states here. All those other states are dark states by their symmetry, by their ring-like symmetry. Although the static disorder or distortion in the ring will give some oscillator strength to the other states, but those are small, not very, not significant. Now this K equals to 0, lowest energy state is a dark state. And it's actually good for lighthouse state, because now energy from here funnels to this state and it can stay here. Does not go away through fluorescence. People have done simulations of energy transfer dynamics in this particular system. And this is work, many groups have done this. And this is the work taken from Van Grondel's group. And they found that this energy transfer dynamics is actually very sensitive to the disorder in the system. If the disorder is severe, you see this kind of localized behavior. The excitation stay here, does not go. This is the site indexes. This is time. So this tells you the population at each site at a specific time here. And this also things like this. So it's evolved wave-like. So excitation here, go here, oscillates between those two, like an rapid oscillation. There's also this kind of diffusive, localized but diffuse along the chain kind of dynamics. Many different dynamics. And certainly, quantum mechanics is needed to describe this kind of time evolution. So it cannot be described just by simply energy hopping from one side to the other side. Particularly in this kind of a situation, quantum coherent evolutions will be important. And we are able to actually decipher the energy transfer dynamics, assign all the different states in LH2 and assign them all the time constants from one state to the other states. What's remarkable here is actually this part. That will be the focus of our next portion of the talk. But recognize that those energy levels, BA50 energy levels, are possible. You have this energy span because strong coupling between them because of delocalization of the acetones. So coherent delocalization of quantum excitations is very important to have this kind of energy landscape and to have energy funnel through those pathways. Okay, this BA100 to BA50 energy transfer rate is also very rapid, and that's actually remarkable. because if you look at the coupling between BA100 to BA50, the coupling is around 20 with number. It's an order of magnitude smaller than BA50 and coupling. And with such kind of small coupling, people tend to think this energy transfer dynamics can be described by so-called Forster resonance energy transfer theory rate approach. But this is not true, because in freight, you have energy spectral overlap term that gives you the rate depends on the spectral overlap term. But if you look at the spectrum of BA50 and BA100, their recognition energy is very small, so absorption spectrum, emission spectrum not very different. They have a very, very small overlap. So if you calculate BA100 to BA50 rate from Forster theory, it's 10 times slower than the numbers that I just gave you before. So it actually takes quite a while for people to recognize this problem. I'm sorry this picture here somehow does not show correctly. But anyway, this is the, I call it donor, I call this acceptor. Okay. And it takes about 10 years for a group of very talented scientists to recognize this and generalize Forster theory to describe this phenomenon. It's called multi-chlorophoric freight formula. This basically considers coupling between each. Now, it recognizes that excitation at the donor group can be delocalized, and the excitation in the acceptor group can also be delocalized. And to describe energy transfer between a delocalized state to another delocalized state, even though the coupling between them are small, you need to sum over all pairs of coupling and then consider coherences between donor group and between acceptor groups. So they came up with this formula. The details are not important, but basically with this formula, these close terms, they are close terms, they represent coherence effect, quantum effect. So with this formula, they go back using the Saint Hamiltonian, calculate the energy transfer rate for the BA100 to BA50 energy transfer. So the rate dot line here is from the Forster picture. This is the rate. And you see a distribution because they consider energy disorder in the system. So they have to have different random numbers in the energy. And then you get a wrong calculation many times to have a distribution of the rates. So here is Forster, very slow. Here is the multi-chlorophoric Forster freight formula. Now it gives you a correct rate that corresponds very well with the experiments. So the basic idea here is consider the localization of states and the multi-chlorophoric freight mechanism. BA100 were able to transfer energy to dark states in the K equals to plus minus 2 and to achieve a very efficient energy transfer from BA100 to BA50. Next one is BA100, intra-ring couplings. They are also very small, very small. Single molecule experiment has shown that BA100 cone for excitation are highly localized. Okay, so people tend to think that this BA100 ring, the outer ring, excitation are localized on a single chromophore and use this picture to do all sorts of calculations, including to simulate the absorption spectrum of the BA100. But all the time, they have in the high energy side, there is a difference. So the dotted line, dots are experimental spectrum, lines are simulations. Here, they cannot get it right here. But around 2006, 2005, Prof. Sylvia and I recognized that if you consider coherence, delocalization in the BA100 ring, and then you run the same very simple simulation over the spectrum, then you get this blue side, blue tail correctly. This is because the disorder is significant. So this is density of state of those acetone states, the density of states. But at different energy, they have an energy dependent. An energy dependent oscillator strength, changing dipole. At low energy, you have a larger changing dipole. At high energy, you have a lower changing dipole. Then you give you this asymmetric band shape. And this is very easy to understand. If you have one BA100 chromophore, another BA100 chromophore, their dipole position are pointing to the center like this. Their coupling is negative, so the low energy side, they have superposition in the same direction. This one is anti-symmetric, minus sign. So this gives you a small changing dipole. This gives you a large changing dipole. Consider this energy-dependent changing dipole. We were able to describe the system very well. And it requires that they are delocalized among at least 2 bacterial cohorts. Use this, we will also be able to explain the energy relaxation or the energy-dependent relaxation rate in the BA100 band. So at higher energy, you have a relaxation. At low energy, because you are sitting on this low energy band, you don't have a relaxation. So this corresponds also very well with experiments. What's more interesting is this. If you consider this excitation delocalized on 2 chlorophyll, and you have 2 states that have very rapid energy conversion between them. So you have an upper energy level, low energy level, energy convert between them rapidly. Either this upper energy level or low energy level can transfer energy to BA50. But one of them will have a larger or faster energy transfer rate. So this builds some sort of robustness into the transfer. BA100 is excited, it can go either this route or this other pathway. Okay, will not be trapped on one of them. And if we calculate the energy transfer time as a function, the distribution of energy transfer time with a monomer model or a single chromophore, this green line here, and this dimer model, this purple line here, and the purple line is more narrow, meaning that the energy transfer rate here, you can make sure that energy can be transferred from BA100 to BA50 within a given time scale. So in conclusion, bacteria knows how to use quantum effect, delocalization of excitations, to achieve highly efficient energy transfer through energy matching, through multi-chlorophylloric effect due to this delocalization of excitations. And the BA100 system actually has a coherent signature, tells you that excitation they are delocalized. So I probably have a few more 10, 15 minutes. Okay. So I will quickly cover a little bit about how we are currently doing in our research group. From what we learned in photosynthetic system, we want to apply those design principles to artificial systems. Now, if you look at how chemists are building artificial light harvesting systems, there is a regular picture over there. They want to build an array of equally spaced regular chain to do light harvesting. Okay, and it's just nature, right? If you have equally spaced, very regular structure like this one, those are synthesized in our department by in Professor Ting Lu's group. They try to have those regular structure, equally spaced structure. It's just nature, because you think this, because energy hopping, energy transfer between them would not have a bottleneck. It's basically some sort of incoherent hopping type of picture. But its regular arrays always provide base light harvesting performance. That's the question we ask. Okay. Now, if you look at photosynthetic complex, this is PS2 core I already showed, and the chromophores within them, you see they are not regular at all. And there are clusters of chromophores, and kind of cluster-like structure is quite apparent here. So we study a simple system, a linear chain. We put 4 chlorophylls on the chain. We fix the end-to-end distance here, and we vary the distance between the donor dimer and the acceptor dimer. So this is donor acceptor defined by their energy. All the parameters we consider are just normal or kind of in the common range of chlorophylls in photosynthetic systems. And we change we can change vary R and theta, this tilt angle of the donor dimer here. So we use some methodology developed in our group to simulate the dynamics. It's quite efficient, so it allows us to perform simulation for a very long time dynamics. This is an example for this four-side model with given geometry. We can calculate if the first side P1 is excited, how energy flow within these four molecules. So this shows you the site population at a given time. This is log scale, and the unit is femtosecond. General trend is in the first few hundreds of femtoseconds. This one is around 200 femtoseconds. At short time, this coherent oscillation, coherent dynamics is significant. And in this case, you see kind of a beating between chromophore 1 and chromophore 2. They are strongly coupled to each other. And then at a later time, you start to see exponential behavior here. Okay. So this exponential growth, transferring energy from the donor pair to the acceptor pair, happens in a much longer time scale. And this simulation goes up to 10 picoseconds. Sometimes we have to go longer. Okay. So some sort of efficient simulation method are required. Okay, run this kind of simulation, record the rate of energy transfer into site 4, and this tells us the end-to-end transfer rate. And we plot this rate, end-to-end transfer rate, as a function of distance between this intra-pair distance and this tilt angle. What's interesting here is for a equally spaced system, you imagine the equally spaced system is 13.13 angstrom here in this geometry. And it's not the optimal geometry. Optimal geometry occurs at around 11 angstrom over here. Okay. And there are some details in there, but our conclusion here is you need to consider quantum coherence effect, the delocalization, superposition of excitations. If you consider the donor states, when they are isolated, there are two energy localized excitations, but they are coupled to each other according to the coupling constant. They split, and this splitting depends on the coupling constant. Stronger coupling, bigger splitting. Weaker coupling, smaller splitting, or even not really splitted. And then you have this acceptor, the same picture here. So if they are dimerized, coupling between donors are stronger, then this splitting is bigger, then you have a big beta energy matching between this lower energy donor state and this higher energy acceptor state. That will allow a faster energy transfer from this donor pair to the acceptor pair. That's the best principle. And there are some details here. Okay, dipole distribution is also important, and the tilt angle affects this, but I won't have time to cover those. This tells us that conventional incoherent hopping picture, energy hop from this side to this side and then to next side, is probably not the most efficient way of thinking about energy transfer. And they actually tends to, if you couple them closer and achieve jump from one delocalized superposition state to another delocalized superposition state, this could be more efficient. So this kind of design principle in incorporating quantum coherence might be useful and important for future design of beta energy materials. We could also use this to explain energy transfer pathways in FMO. This has been identified by two-dimensional electronic spectroscopy. The FMO, this denotes FMO, transfer energy from base plate to reaction center. Two pathways, especially this pair, 5,6 to 4,7 to site 3, is shown here, 5,6, 4,7. So this pair and this pair, they split, they actually dimerize to increase the energy splitting here, allow this to overlap and have a rapid energy transfer in this pathway. Now, the other part of the research I want to share with you has to do with network. So this is the photosystem 1 complex. It contains 96 cofields, very complex network. Those are reaction centers sitting in between. If I connect chlorophylls, I put lines between chlorophylls according to their intermechanism distance, you see a complex network like this. And I think this is really a very interesting system. I call it paradigmatic scenario of transport phenomena in noisy environments, because you have all sorts of disordered electronic coupling and acetones in the system. It forms a complex network. This system has disorder, static disorder, dynamical disorder. Okay. And embedded within a wet and warm protein environments. And also you need to consider quantum coherence effect between these transfers. So this will be a very interesting system to explore and to study, to understand transport phenomena in noisy or disordered environments. This system has also been studied before. So the first question we want to ask is whether or not Lahab-Stein in PS1 is efficient. Everybody says Lahab-Stein in photosynthesis are efficient, is efficient, but is that true? We want to compare, we want to ask this question by comparing this structure to random networks. Okay. If we can randomly generate a network and achieve the same efficiency, then it's not efficient at all, right? So, but you cannot compare it to arbitrary random networks. Okay, the key is you need to compare apple to apples, not apple to oranges. Otherwise, you are not doing any good. So we carefully select. This is PS1 chlorophyll arrangements, and this box is the box that we select to generate random network within it. And we select this box because when we generate a random network in a box and measure the chlorophyll, this pairwise distance distribution. This is a green line here. It reproduces the distance distribution in PS1. Okay, so we believe this kind of gives us a proper system, a proper basis to compare, and then calculated trapping time using our method. Calculated trapping time in PS1 is around 30 picoseconds. That's similar to what's measured experimentally. So we can generate, put in 96, we fix the reaction center chlorophylls, or fix those. And we randomly put in sites in the box. And then with each geometry, we can calculate the rate. So we then calculate a quantum yield. So we have a quantum yield and the distribution of those random networks. There's a blue line here. And the PS1 actually gives us a quite high efficiency, 97%, 97.5%. It's among the top 3% of those random networks. So they are not that difficult to sample, but indeed they are efficient. They are efficient. Okay. What's more interesting is if we change the number of chlorophylls in this same box. If you put in smaller number of chlorophyll, they are far away from each other, so the energy transfer efficiency is low. You increase the chlorophylls, the efficiency increases. And then when you keep increasing to a very large number, excitation actually get lost in there. Okay? So you see some sort of optimal density or optimal number of chlorophylls in this size of the box that will produce the pairwise distribution in PS1. And the number here is the real photosynthetic system. The real PS1 has 96 chlorophylls. Very close to the maximum over here. Okay. And we can actually test other systems. So LSC2, sorry, this should be LSC2. And FMO, they are globular, so spherical proteins. So we use a spherical, a sphere to model with a size close to LC2 and FMO. LC2 monomer. This one is bigger, FMO is smaller. And applying the same trick, we found that for this LSC2 model with this curve, FMO model with this curve, this 7, this is what's found in real system, this 14 what's been found in real system. They are close to the saturation line. They are too small, they don't have this kind of decay. but they almost saturate here. And you can imagine that in a biological setup, if you can perform